Our chemistry, this is our next lesson in the foundations unit, and it is on ionization energy. Okay, so here's an example. What is the Coulombic attractive force between a proton and an electron? Remember, they both have the same charge, but opposite, and separated by 0.71 nanometers. So how would you set this up as a problem using that formula? There's the formula. And here's how you'd set it up. K is Coulomb's constant, 8.99 times 10 to the 9th. Q1 is the charge on the proton. Q2 is the charge on the electron. It doesn't matter which order you put those in. And D is the distance between them, which is 0.71 times 10 to the minus 9th meters. And then you have to square that number. So multiply the coefficients, 8.99, 1.602, negative 1.602, divided by 0.71 squared, and you will get 45.7686. Now I've neglected the minus sign at this point because the force is in both directions, and we won't get into that concept right now. The exponents, you add the ones on the top, 9 minus 19, minus 19, and then the one on the bottom is a little bit tricky. It's negative 9 squared, which is negative 18, but then you have to subtract the negative 18. It becomes positive 18. So your exponent becomes negative 11. And so when you put those together and adjust the decimal, you get 4.6 times 10 to the minus 10th coulombs. Forces act in pairs, equal and opposite in direction, so it doesn't matter whether you call it positive or negative. One of them is positive, one of them is negative. That's a point that we won't get into any deeper than that. Okay, lithium has an atomic number of 3. The atomic number is called the Z number. The atomic number is the number of protons in the atom of an element. So we've seen this diagram before of lithium, 3 protons, 3 electrons, and this particular isotope has 4 neutrons. The core electrons are the electrons inside the valence orbital. The core electrons are said to screen or shield the valence electron from the pull of the protons in the nucleus. Core electrons are all electrons inside of the valence orbital. These electrons, the 2 on the first orbital, screen the valence electron from the pull of the protons. Valence electron is, of course, the one that's in the valence orbital. So you can see that the 2 that are in the first orbital are blocking the valence electron from feeling the pull of those 3 protons. So effectively 2 of those protons are canceled out. Let's see how that works. Effective Z number, Z effective, measures how much of the pull of the protons an electron feels. So Z effective is the Z number. It's the actual atomic number. In this case it's 3, minus the number of core electrons, which you can see those are the ones circled, that's 2. So 3 minus 2 is 1. So although lithium has 3 protons, its valence electron feels the effective pull of only 1 proton. It's as though those 2 got canceled out and 2 of the protons got canceled out, and now you have 1 proton, 1 electron, so that 1 electron feels the pull of just 1 proton. What does that mean? It means that it's not being held as tightly as otherwise you would think an electron in an atom with 3 protons would be held. Ionization energy is the amount of energy that is required to pull an electron away from its atom. The man represents ionization energy. The ionization energy must have a greater pull on the electron than the protons do. So there goes the electron, it's being pulled away. Ionization energy is also called electron binding energy. Ionization energy increases across the periodic table from left to right and increases going up. Ionization energy increases up a group and to the right in a period. So there you see a perspective view of ionization energy. So you can see the elements in the upper right-hand corner of the periodic table have the greatest ionization energy. Lowest ionization energies on the lower left, highest ionization energies on the upper right. Ionization energies are lowest when an electron is furthest away from the nucleus, that is, the atom has more orbitals. 2, the nucleus has fewer protons. So let's compare lithium on the left there and fluorine way over on the right, number 9. Lithium has a lower ionization energy for its valence electron than fluorine because its valence electron is the same distance from the nucleus as fluorine's, because they both have 2 orbitals, but lithium has only 3 protons to attract the electron, while fluorine has 9 to attract its electrons. So therefore fluorine will have a higher ionization energy than lithium. So the Z effective of lithium we just calculated earlier is 1. Now fluorine has a Z effective of 7 because it has 9 protons, 2 core electrons, same number as lithium, so 9 minus 2 is 7. So the valence electrons, the second orbital electrons in fluorine, feel much stronger pull than those of lithium. Bromine, let's go down the column there. Bromine has a lower ionization energy for its valence electrons than fluorine because it has more orbitals. So its valence electrons are farther from the nucleus. Each electron in an atom has its own ionization energy, and we refer to that as IE. These are called the first ionization energy for the first electron ionized, the second ionization energy for the second electron, and so forth. The valence electron of lithium has the lowest ionization energy. It is the easiest to pull away because it is shielded from the nucleus and has a Z effective of 1. It's also simply a farther distance from the nucleus, and we'll talk about that concept that the distance also affects the ionization energy. So there goes the outer electron, the valence electron, and it has an ionization energy, and this is well known. It's been measured, and that's 520.2 kilojoules per mole. Now that's a strange unit of measure you're not familiar with, but it simply means how much energy it takes to pull away an electron. Note that the units kilojoule per mole are a measure of energy we will discuss later. Each electron in an atom has its own ionization energy. We've read that. Okay, so the second electron of lithium has a much higher ionization energy. It is not shielded from the nucleus, and it's closer to the nucleus, so it feels the pull of 3 protons. So there goes the second one. The second ionization ionization energy of lithium is 7,298, a much higher number. You don't need to have these numbers memorized, okay? Okay, and finally, the third ionization energy. The last electron of lithium has the highest ionization energy. It is not shielded from the nucleus and feels the pull of all 3 protons. In addition, it does not feel repelled by the other first orbital electron. So its ionization energy is 11,815. So it takes much more energy to pull that last electron away. Okay, an electron is held with a binding energy that is a negative number. Ionization energy is a positive number that cancels the binding energy of the protons and releases the electron. So the binding energy of this electron is negative 520.2 kilojoules per mole. The ionization energy of positive 520 comes in, and that can remove that electron. Energy into an atom is positive, like money into your bank account. Energy out of an atom is negative, like money out of your bank account. All right, and that takes care of our lesson on ionization energy. We will talk about this quite a bit during this course.